Hello world, it's Craig. In the last video, we discussed the 8008 clock requirements and expanded outward from the tick of the crystal to a T-state, which is the smallest slices of time that we generally talk about. In this video, we're going to start at the opposite end and work to smaller and smaller time slices until we get to where we left off in the last video. I did some videos a few years back on 8008 assembly, and from there, I'm going to jump to what happens at a single processor instruction, and we'll break that instruction down into subcycles, then break those subcycles down into T-states. Then I'll define it later, but a T-state is the period that was defined by the sync signal where we finished the last video. So one period of the sync signal is one T-state. We ignore the fact that sync may be delayed by 700 nanoseconds, and we treat it as an ideal signal, and it's up to the hardware designer to deal with all the limitations of the sync and the proper timing and so forth. Then let's start with a single instruction and work our way down to these smaller time slices. When we write in assembly, we put one instruction per line, and that instruction will have the instruction mnemonic followed by any operands. Or there may just be the mnemonic if there's no operands are needed with that particular instruction. Or a mnemonic and 2 bytes in that operand, like a jump where the operand is the 2-byte destination address. Then we take that source file and we assemble it. And the assembler creates the output file, for example, an Intel hex file. In doing that, the assembler takes the mnemonic and it creates the machine instruction, which is the binary data that the processor can actually interpret. And it's that machine instruction that sets the internal configuration and allows that instruction to be executed by the processor. The assembler has a little trick up its sleeve because sometimes what appears to be a 2-byte instruction, so it'll have a mnemonic and an operand that looks like 2 bytes, can actually be reduced to a single byte. And so let's take a register move, for example. The 8008 has old assembly mnemonics and syntax, and it has a new mnemonic and syntax. And if we look at the new assembly mnemonics and syntax, you would have something like this. You would have a MOV as the instruction mnemonic, and then A, B as the operand. So MOV is the mnemonic for move, and A, B is the operand telling the move instruction, it qualifies that move instruction, to take the value in B and duplicate it over in the register A. And if we look at this, it looks like a 2-byte instruction because there's the mnemonic and then there's that operand. But if we look at the old load instruction syntax, this would just be LAB, which in a similar fashion means load A with the contents of B. But looking at the old instruction, it gives us the idea that maybe this is actually only a 1-byte instruction because there's no operands in this old format. It's just LAB. Everything's contained in that. In fact, this is the case. Either one of those, the move A, B or the LAB, will result in the machine instruction 301 in octal, which is only 1 byte. Now, most of the 8008 instructions are 1-byte instructions, and many are reduced from a mnemonic and an operand if you're using the new mnemonics and the new syntax. But if you're using the old mnemonic, then you can more easily see that these are 1-byte instructions because they won't have an operand with it. You know, the new mnemonic and syntax was, of course, introduced so that it could be consistent with the 8080 and beyond. Now, I'm going into all of this instruction business because the processor needs to be able to handle every condition that comes along, and the number of bytes in an instruction is a big variable as far as the processor is concerned. Your program wouldn't get very far if the processor didn't know which bytes are instructions and which bytes were data. And that's exactly what would happen if it didn't know how many data bytes followed each particular instruction. So we talked about these 1-byte instruction, and of course there are actual 2-byte instructions where the machine instruction is the first byte and the operand is a data byte that will be put into the subsequent memory location. A move immediate is a good example of that. Your instruction will be MVI A, and then some 8-bit data. And in old format, it would be LAI, or load A immediate, and then you would have a data byte as the operand. Either way, the first memory location will have the instruction 006 in octal, and the next byte in memory will be whatever that data byte was, whatever you had for your D8. So that will actually take 2 bytes in memory for that instruction. Then there's the 3-byte instructions like jump. jump 0, 1, 2, 3 for a non-conditional jump, we'll have the machine instruction 104 for the jump, and then the next 2 bytes will be 023 and 001 for the destination address in Little Indian style, of course. This state transition table found in the 8008 data books is one of the handiest, useful, and informative tables in the entire 8008 library. From it, we can see the 8008 has got 27 instruction groups, and we can see that there are 18 of these that are 1-byte instructions. There's 3 that are 2-byte instructions, and 6 of them are 3-byte instructions. And we'll revisit this table as we bring up other aspects of the 8008 processor states. When the processor is working on that one line of our assembly code, whether it be 1 byte, 2 bytes, or 3 bytes, it retrieves and handles these bytes in that line one at a time. So it gets the first byte and it deals with it. The processor now knows if there's another byte. If there is another byte, it gets that byte and it deals with it. And then if there's a third byte, it'll read that byte and deal with it. So it deals with these bytes sequentially one at a time. And that whole time the processor is completing your single line of code on the 8008, that sequence is called a machine cycle. So that period of time that it's doing all of those fetches of your machine instruction and any operands that are there, that is on the 8008 called a machine cycle. Now don't get too emotionally attached to that term of machine cycle to mean the entire time that the processor is executing your line of code, because Intel is going to change that definition when the 8080 comes along. The new name for that exact same thing will be an instruction cycle. For that time period, the processor is executing your instruction, meaning the whole time it's getting the machine instruction and any operand bytes and then executing that instruction. And that term, it obviously makes much more sense. And now if we've got a 3-byte instruction, the 8008 machine cycle is the fetching and executing of the instruction, but we know this is done sequentially, meaning the bytes are read in one at a time. So for a 3-byte instruction, that whole process would take 3 cycles, and that seems logical enough. If it's a 2-byte instruction, we would expect it to obviously take 2 cycles, and that's true unless it's one of those 2-byte instructions that actually takes 3 cycles to complete. And then there's some more tomfoolery going on with 1-byte instructions, since sometimes they can take a single cycle and sometimes they can take 2 cycles to complete. And that's exactly when this transition state sequence table comes in so handy. We can see here how many cycles each instruction takes. For the 8008, these cycles, where it's handling a byte, are called subcycles. The term subcycles will go away when the 8080 is introduced, so there's no danger of confusing subcycles with anything else, but what we're calling subcycles on the 8008 become machine cycles on the 8080 and later. And this all means that starting with the 8080's documentation, things get bumped down one. The new term instruction cycle is introduced at the top. Machine cycle term gets bumped down to take the place of subcycles, and the next smaller unit, the T-state, stays the same as it was before. So this can be a bit confusing if you're going between 8080 and 8008 things, because that terminology actually does change. And the term subcycles, it nearly goes away as soon as they put out the 8080 documentation, but not quite. If we look in the instruction transition state sequence table, someone forgot to update the notes for the 8080, and so the term subcycle still appears there. If you ever find yourself in this argument, there's 10 places left in the 8080 manual where they're still calling these subcycles, and they didn't change them to machine cycles. And they didn't fix that in the MCS 80/85 manual, where there's still those same 10 places in the notes where the term subcycle is used. They finally stopped using that term subcycle in the MCS 85 manual. Well, actually, in the MCS 85 manual, they took out the whole table, so I don't think that counts as fixing the mistake. And it's unfortunate because that was a very useful table, and I'm disappointed because I thought it brought a lot of clarity and understanding to the processor operation. So it's a shame that they dropped that with the 8085. But I may occasionally slip up and call subcycles machine cycles, or call machine cycles instruction cycles. So, as always, expect at least the normal number of misspeaking slip-ups in this video. So let's focus on these subcycles. As you can imagine, it's critical for the entire system to know what the processor is doing as it's fetching these instructions and exchanging data with memory, or when it's reading or writing to an I/O port for that matter. There's 4 top-level categories the processor can be doing. It can be fetching an instruction, It can be reading from memory, it can be writing to memory, or it can be doing I/O with a port. And each of these subcycles have a name, and all the documentation for the 8008 refers to these names, so it's important to understand and keep them apart. And fortunately, these names are easy. If the processor is fetching an instruction, that subcycle is called a processor cycle instruction, or a PCI. If the processor is reading from memory, that subcycle is a processor cycle read, or a PCR. If the processor is writing to memory, the subcycle is called a processor cycle write, or PCW. And finally, if the processor is doing port I/O, the subcycle is a processor cycle control, or a PCC. Now, the 8008 puts out 2 bits that identify the type of the subcycle, and these are called the cycle control coding, or the CC bits. The low bit is CC0 and the higher bit is CC1, until it frequently puts the lower bit first or on the left in truth tables, and I'm not really sure why, but this is out of the data book. This is what the truth table will look like. We've got CC0, CC1, and what subcycle it is. 00 is a PCI, or an instruction fetch. 01 is a PCR, or a memory read. 10 is the PCC, or an I/O control cycle. And a 11 is the PCW, or a memory write. Now, like the 8080, these 2 bits come out as status bits during a subcycle, but since the 8008 is only a 14-bit processor, meaning it's only got a 14-bit program counter, when it puts out the high portion of the address, it only needs to use 6 of the bits in that byte. So the processor takes the unused bits and it fills them with the encoded subcycle type. So it goes like this. In every machine state or machine instruction, using the new parlance, the first step will be for the processor to put the low address byte of the program counter onto the bus. The program counter, as I hope you understand, is just a bookmark that tells the processor where it's getting its next byte from memory. In the 8008, it's a 14-bit internal register. So in this case, it's putting the low byte of the address of the instruction that needs to be fetched and then executed. After the low byte goes on to the 8008 bus, and the rest of the system hardware deals with it, for example, it latches it onto an address bus to be delivered somewhere else, the low byte of the program counter is incremented. And then the top 2 bits of the high byte are filled with these cycle control codes, or these CC bits. So we've got the 6 bits of address, and then on the top, we fill in 2 bits of these 2 CC bits. And those 2 bits define what type of a subcycle this is. And then this byte is put out onto the 8008 bus, and presumably it's latched by the system as the high part of the address. And then any carry that was generated from the low byte program counter being incremented is now added to the high 6 bits of the program counter. And the program counter now contains the address of the next byte in memory. At this point, the hardware can skim off and read those CC bits so that it can identify what type of a cycle this is going to be, and the glue logic can then deal with that cycle. Now let's look at how the Intellect 8, the IMM 882 handles these 2 control or CC bits. As I showed in the last video, these bits are latched along with the 6 address bits in this pair of 8 T10s. So they're now latched and fixed for this subcycle. And remember that every subcycle is going to have their own CC bits to indicate what type of subcycle that is. And the first cycle in every machine cycle, or instruction cycle, is going to be the instruction fetch, or the PCI. So the 2 bits are going to be 00 from our little table that we just had. And you can see in the 882 schematics that these 2 bits are peeled off as CC0 and CC1. They go down to D10, which is a 3205, and that's a 3 to 8 decoder or a 1 of 8 decoder, whichever term you prefer, as the lowest 2 bits. And that selects one of the bottom 4 outputs, which are not PCI, not PCC, not PCR, and not PCW. And here the bits are in the conventional order, so CC0 controls A0, CC1 controls A1. A2 is just tied low since we're not using the top 4 bits of this decoder. So now with this decoder D10, now the board has determined what type of a cycle is happening. And in a later video, we'll chase that down when we start talking about glue logic, and we'll come back and we'll take off at this decoder to see how that information is used on the rest of the board. But for now, let's get back to our subcycle discussion because this video was about the processor states. The first subcycle is always going to be a PCI to fetch the instruction. And then the next subcycle, sticking with our move immediate example where we need to now get a data byte to be moved into the register, this next subcycle will be a memory read or a PCR. If this were a jump with the 14-bit address that takes the better part of 2 bytes, then the next 2 cycles would both be PCRs to read the low part of the destination address and the high part of the destination address. And so that machine cycle or that machine instruction would be a PCI and then 2 PCRs for that jump instruction. And if this were an I/O instruction, then after the PCI, the second subcycle would be a PCC, which was the processor cycle control. And this is a great one. If our instruction were a move immediate to memory, so it's going to be an MVI, M, and then a data byte. Here's an example of a 2-byte instruction that takes 3 cycles. The PCI is first, of course. The MVI M is 076 in octal. And then it needs to read the immediate data, the D8 data from memory. So that's going to be a PCR, but then it needs to write that data back into memory. And so that's a PCW. So here we've got a PCI, a PCR, and a PCW. And that's a very nice example all the way around. Again, it's critical that when it interprets the instruction in the PCI, the 8008 needs to determine if there's going to be more subcycles left needed to complete that instruction. Maybe, for example, it's just done with the PCI and the next subcycle is just another PCI. Because of the 27 instruction types, not quite half of them, there were 13 of them that are completed with just the first PCI. There's 6 of those that will require 2 subcycles. 2 of these are the port instructions, which will be a PCI and a PCC. And I think that leaves 7, and those will all require 3 subcycles. All the jumps will be PCI, PCR, PCR, but the unique move immediate to M that I mentioned earlier is a PCI, PCR, PCW, which is a real fun one. Well, I think that's a good time to end the first half of this video on the process cycles for the 8008. So we've gone all the way from the program and looking at a single instruction, which is referred to as a machine cycle on the 8008. We looked at the subcycles. We know how many bytes each of those takes and how many subcycles each of those take by looking at this state transition table. So in the second half of this video, we're going to be continuing to dive in and look at smaller and smaller time slices and the machine states of the 8008. So that's what we'll do in the next video. Thanks for watching. I appreciate your feedback. Remember, this channel is entirely fueled by likes, feedback, shares, and so forth. Talk with you later. Bye-bye.